So this morning, I would like to speak a little bit about the scientific data management using JavaScript. It's true that JavaScript is not really the language you would think about for data processing, but somehow we try to do everything using this language. So it's really a lot of people sharing the same interests from industry, from other universities that will contribute to those open source libraries in JavaScript that are reusable. So the problem I would focus today, it's how we store the original data and how we can create fair data to be reused by other people. So let's say you have a battery, you make some analysis, maybe IV curves, and the idea is that if you have a folder with those data, you can somehow store in a database the original data. And hopefully you have a QR code, data matrix code, so that you have a good traceability. And maybe you use another software, another experiment, and somehow it's saved in a folder, and we can import it in a database. Or maybe it may be images, NMR spectra, infrared spectra, whatever you want. The problem here is that all those data have different formats. And what we need somehow to do, if you want to easily display them, compare them, it's to normalize those data, those spectra, those measurements. And if we do this step, it's easy from an API to make some machine learning software because the data are there, they are in a similar format, so we can easily get them and make some advanced processing. But our goal is also to be able to process those data directly in the web browser. And that's the main reason for JavaScript. So the goal is to be able to replace the applications you need today to install on your computer and just use the web browser. So one example, it's dev.nmarium.org. Everything I will show you, it's of course open source. So this is a web application that allows to easily compare a lot of NMR spectra. So for example, here, I just loaded 13 or 11 NMR spectra of ecstasy pills, but you can still zoom in the browser and compare those spectra. And this is something important to be able to compare a lot of spectra, especially when you make parallel synthesis. But you can display the spectra, but you are also able to process the spectra in the browser. Fourier transform, baseline correction, advanced peak picking. So something you would do if you are playing with NMR spectra, well, it's to make peak picking. The system will try to understand the multiplicity of those peaks. In this case, it found out it's a doublet of doublet of doublet, and you even have the possibility to display the splitting of the different couplings, which is quite useful also for teaching. So you can display and process 1D spectra, but as well, you are able to load 1D and 2D spectra. So in this case, citizen. So we have the proton, we have the carbon, we have here the COSY. You can zoom in the COSY, you have the 1D traces, you can vertical scale the COSY, or you can even superimpose 2D, so in this case, HMBC and HSQC. So one question that may raise is how we are doing this kind of development. And actually, we are doing fair development. It's not fair data, but it's really small modules that are findable, accessible, interoperable, and reusable. So instead of making one huge project that would be a big lab notebook, well, we will try to make small modules that share the same format, share the same data kind. And if I take back the NMarium project, so this application to process NMR spectra, well, actually this project relies on 60 of our libraries. And we are not the only one to use those libraries. We did them, we published them, but JCAM converter is reused by ChemMotion. If I take ML Matrix, we have several million downloads per year of this library ML Matrix. So the main advantage is that people are reusing those small libraries, and it means somehow it's debugged, or it's we outsource the debugging because either people find bugs, fill reports, or contribute to those projects. So how we can manage so many projects? Well, we have kind of very strict rules, a lot of test cases. We tried, here is the JCAM converter, to have a high coverage of the tests. So in this case, we have over 90% of the code is being tested. We have, of course, traceability. We know when the coverage increase, decrease, and using GitHub, you have the changes in one click that has been done on this code. More recently, what we are also doing is to publish the code on Zenodo. So with each release, automatically, there is a new DOI that is assigned to this code so that you can only get a specific version from Zenodo, but you can also cite it in any publication. So I would like to focus now on one very specific problem, is this data normalization, and mainly in the field of spectra. We try not to use spectra anymore, but measurements, because TGA is not really a spectrum, or DSC, or there are plenty of analyses that are not spectra. So we have three projects that are a little bit the core of all those developments. One of them is the data schema. How do we save, where do we save the information about a sample? In which part of a JSON we store the mol file, the NMR spectra, the images, the TGA, the IV curves, everything. We have another project that will define some TypeScript definition so that all the other projects can reuse those types, and those projects are able to speak between each other, use the same kind of object. And we have the base analysis, that is the project that will deal with curves, IV curves, NMR spectra, infrared spectra. So an analysis will contain measurements, and a measurement will have a data type and a description about this measurement. We will have some settings. Settings will contain information about the instrument, brand, model, but also some information important for this specific kind of analysis. If I make an infrared spectrum, well, maybe I would like to know the temperature. Or if I make a boiling point, I would like to know the pressure, or things like that. Each measurement will yield some results, and those results are stored in variables. And variables will have a specific unit and will contain the actual data. So if I'm speaking about an infrared spectrum, I would have on the x-axis the wave number, and on the y-axis, for example, the transmittance. We will have some meta information. A lot of instruments generate data. Maybe they make some fitting of the curve, they calculate some inflection points, or they acquire the temperature during the experiment. All the meta information will end up here. And finally, we will have some derived data, so that are automatically generated. For example, again, in infrared, I would like to have a peak picking, but I would like that the peak picking is stored in my database because I would like to be able to search for it. So those are derived information. How we create an analysis? Well, it's a simple text file. So we have a way to create this kind of object. It's an instance of a class, JavaScript class. We are able to create an analysis from a text file. But we are also able to create from JCAMs, or maybe from a JSON, or some proprietary formats. An analysis can be saved itself as a JCAM or as a JSON. But often you would like to display those analyses. You would like to superimpose many infrared spectra, NMR spectra. Well, we have two libraries. One is JSGraph and one is ReactPlot. There is a way to directly generate the right format so that we can display those data in the web browser. And finally, this base analysis, this core project, also have many tools that allow us to make peak picking, baseline correction, and many other standardization on your data. So a lot of work. Yeah, why JCamp? Actually, JCamp is definitely not a new file format. It really goes back to the punch card, and some characteristic of this file format, it's because of the punch cards, like the limitation, theoretical limitation of a line to 80 characters, for example. So what's nice in a JCamp, it's a text file, so you can open it. You can open it, but also you can open it in any language because there are converters in Python, in R, in MATLAB. You can just open this kind of file. And this file will contain a section with all the data, in this case, simple peaks, a section that contains general information and somehow normalized information, like the number of points, the first value, last value, and so on. But in this format, you can add as many meta information as you wish. So out of the box, you can put the sharp $, and start to add more information. Should have put the pressure with 20 degrees, but you can add more meta information directly in this text file. So if we have a specific kind of analysis, thermogravimetric analysis, for example, well, the instrument generates some strange files, Excel, text, some proprietary format. What we will do is to create a TGA analysis project and making some new converters. So for example, from NETCH or from some other instruments, so that we can create this object analysis and save in the database, not the original data, but a JCamp. And if we have those JCamp, all our tools will work out of the box in order to process those data. So we created over 200 libraries, small project, test, reused, and some libraries will parse data, will generate JCamps. Some of them will parse images or process images, region of interest, and so on. We have plenty of parser for specific formats like the GEOL, Bruker, WDF, that is Raman, SPC for infrared, and the data for mass. NetCDF also used for mass, VAMAS for X-ray. And then we also have plenty of libraries, reusable libraries for machine learning, dealing with matrices, PCAO, PLS, global spectra deconvolution, and so on. So that's a quick overview about the way we program, the way we tackle this problem, creating small reusable libraries in order to make more complex projects.